Well, good morning, class, or good afternoon, whatever time it might be for you. I hope you're enjoying your spring break. And we're going into a new chapter, chapter 17. It's part of Unit 8, and we're going to the next level beyond electrostatics. And this is the part of the curriculum when we explore charges that are moving instead of being stationary. Electrostatics means static, staying put, and current electricity, current meaning it's moving, it's charges in motion. So just an overview of the content. We're going to solve some problems related to current, electrical work and power, solve some problems involving simple DC circuits, direct current circuits, analyze data from a circuit using Ohm's law, and we're going to connect resistors in parallel and show how to manipulate the mathematics of connecting resistors in parallel and connecting resistors in series and parallel. Well, this chapter is a very foundational chapter for us, and it develops a basic understanding of how electrical energy is used in our daily lives. We walk through some labs as the semester rolls along, and to enhance our understanding of this very important part of electricity. So I want you to read chapter 17 in its entirety, and the content of this slideshow is only meant to be a supplement to the content of your text and not a replacement. So let's go over current, voltage, and resistance. Current is charge in motion, since protons are locked into the nucleus and the lattice of the crystal or the material that it is that it's in. It's not very mobile. The charge in motion is actually the very mobile electron. Electrons are very small, about 1/2000th the mass of the proton or neutron. And the electrons are not bound by the strong nuclear force. Only the protons and neutrons are bound by that very strong force which binds the nucleons. And this strong force has very limited range, and its range is just barely beyond the boundaries of the nucleus. And since the electrons exist in this cloud around the nucleus about 50 times the dimension of the nucleus, it's not affected at all by the strong force. So that's the current, charges in motion. Now we can picture voltage as a pressure that exists between the extent of any conductor that provides the motive force, the electromotive force for electrons to flow. One part of the circuit, which is the power source which provides this voltage, is the one that provides this pressure. Another part is a wire made from a conductive metal which connects the circuit components. And for the purpose of our analysis, we will consider this wire to have zero resistance for now. It's sort of an idealized wire. In reality, the wire itself has resistance, but we won't consider that resistance for now. And that part of the circuit which consumes the electrical energy for a certain task, for example, a light or some sort of a device that consumes electricity to perform a needed task. And this is the resistance because it converts that electrical energy into whatever task needs to be done, whether it's heating, lighting, or something. So that's current, voltage, and resistance. If you recall, in electrostatics, we have these isolated charges in space, and because they're stationary in space, there's a force between them. In this case, there's an attractive force that attracts these negative charges to the positive charges, and that force is the electrostatic force. When we consider wires in electricity, we have these charges now are free electrons that are in a wire. And there's a lot of them because there's a lot of electrons in matter. For example, just a 12 gauge wire, which is roughly 1/10 of an inch in diameter, contains 6 times 10 to the 23 atoms, which means that you have on the outermost shell, you have these 6 times 10 to the 23 electrons, just in a piece of wire that's only 1/10 of an inch thick or in diameter. So going back to the slideshow, the unit of the current is the ampere. That's this. The ampere is defined as a coulomb per second. Now, what is a coulomb? A coulomb consists of 6.25 e to the 18th electrons, each having a charge of 1.6 e to the minus 19th coulomb. So that is the definition of 1 coulomb. Therefore, 1 ampere then involves the movement of 6.25 e to the 18th electrons per second. So that's how many electrons are moving for 1 ampere. And 1 ampere is not a lot of current. Like your typical household outlet is a 15 ampere outlet in AC. Each copper atom has 29 protons, 29 electrons. There are roughly 2.78 times 10 to the 23rd atoms across the cross-section of a 12-gauge copper wire. Since each atom has 29 electrons, there are plenty of electrons in the cross-section that can be mobilized in a 12-gauge wire. So contrary to popular belief, the drift velocity of electrons in copper wires is rather slow. It's in the order of a few millimeters per second. Therefore, the electrons that are moving in your appliances or in your light are not the ones from the power plant generating the electricity, but they're the ones contained in the wires that are in your house, in your walls, when it was first built. So that's how that works. The energy transfer is quite fast, just below the speed of light, yet the electrons themselves are very, very slow. So let's consider what conservation laws apply for electromagnetism. So there's the conservation of energy. Energy cannot be created or destroyed. It can only change forms. And there's also conservation of charge. Charge cannot be created or destroyed. It can only be transferred from one region to another. Why is electrical energy fast while electrons moving is slow? The answer is the electric field propagation is only limited by the permittivity of space around the conductor, while the electrons have to move through the crystal lattice of the atoms in the conductor. And the speed of the electric field is nearly the speed of light because of that. And so the electric field is what really propagates the energy, not the electrons. The electrons are it's part of the system. It's actually what creates the electric field is the electrons themselves, the moving charges, but the energy is transferred through the electric field and not from the electrons. Now we'll talk about voltage, which is potential difference. Voltage and potential difference are one and the same. And resistance is the resistance to electron flow in matter, in materials such as wires or whatever matter. Everything will have some sort of resistance. The difference in potential is known as the voltage. This voltage provides the pressure to mobilize the electron flow. The higher the voltage, the higher the electron flow or the current, and this proportionality is known as Ohm's law. Ohm's law states that the voltage is proportional to the current, and proportionality is dictated by the resistance to the motion of electrons by the part of the circuit dissipating the electrical energy, which is the resistance. In equation form, it's V is equal to current times resistance, where V is the voltage and I is the current and R is the resistance. The energy transfers fast, just below the speed of light, yet the electrons themselves, of course, are very slow. The resistance depends on the resistivity of the material, the cross-sectional area for the flow of electrons, and the length of the conductor. So in equation form, resistance is equal to resistivity rho times the area divided by the length. And resistance exists in all components of the circuit. So what is voltage? Voltage is work or energy per unit charge, and that is joules per coulomb, which means that if you rewrite the equation and you have work or energy on one side and voltage on the other, then the work is equal to voltage times the charge. Voltage times charge is the work. Since power is the rate of change of energy, so it's joules per second is a watt. 1 watt is 1 joule per second is the rate of work. Then it follows that the power is the rate of change of work with respect to time, and that is equal to voltage, which is that same equation here, times the change in charge divided by time. So it's charge per second, which is actually current. And this is how we derive Ohm's law. Ohm's law is just an extension of conservation of energy and conservation of charge all in one equation. So power means voltage times current, and since voltage is equal to current times resistance, which is Ohm's law, then power is equal to, this is the voltage, and it's multiplied by current, and since you have two current terms here, which becomes square term, it's going to be a current squared times the resistance. So this is called the I squared R power dissipation law. Energy is power times time. It's joules times seconds. So joules, watts is, energy is joules, is watts times seconds. So 1 joule is 1 watt second. So you have to sort of remember these relationships and sort of memorize them because it becomes important when it comes to solving problems, and especially solving problems under pressure, like in a test situation. Now let's talk about resistors. Resistors are these squiggly lines. They're called resistors. And they're the symbols used for them are R, R1, R sub 2, R sub 3. So these squiggly lines are resistances. And this symbol here is a power source. In this case, it's a direct current source. It's a battery. So it's a direct current going from the positive is the large one, and the small one is the negative. So the flow is from positive through the resistance 2, resistance 3, and back to the battery, to the negative terminal of the battery. So the voltage is the total voltage on the battery is going to be the sum of the pressure, or the voltage drops, which is the pressure drop in essence. The voltage drop through each resistor. So this voltage 1 is going to be I times R1, and it's going to be one current flows through the entire circuit. Only one current. The total circuit current is I sub B is equal to the current through resistor 1, resistor 2, and resistor 3. So they're all the same. And the total resistance is the sum of the resistances. So the equivalent resistance would be R1 plus R2 plus R3. So the total voltage is the current times the total resistance. So this V here and this VB here are one and the same. And each resistor will have a voltage drop across it. And the sum of the voltage drops are going to sum up to V sub B, which is the battery voltage. So this is a direct current circuit. We're saying that the wires connecting these resistances to the battery are currently zero resistance. At least that's what we're defining it. In reality, there's some resistance there, but we're not bookkeeping it. Now let's look at the right side. These are parallel resistors. The resistances are in parallel. This R1, R2, and R3 are in parallel. The voltage drop going from this leg to this leg is the same as the voltage drop from here to here, here to here, because they're in parallel. The voltage difference with resistances in parallel are the same. So the voltages V1, V2, and V3 are the same. Just like the currents are the same in this series circuit, in the parallel circuit, the currents are not the same because the currents can choose to go in proportion to the resistances, in which case the currents will have to sum up. So this the current coming out of here plus the current coming out of here plus the current coming out of here is going to be the same as the total current. And the resistances add in this way. So 1 over the equivalent resistance is equal to the sum of the reciprocals of the resistances. 1 over R1, 1 over R2, and 1 over R3. So this R here is really the equivalent resistance. V is equal to IR. The I is the sum of the currents, and the R is the equivalent resistances. So when you have a complicated circuit that you have to solve involving combinations of series and parallel resistances, you have to reduce it first into something simpler so that you can add them up as series resistances instead of parallel resistances. And we'll go through an example in a little while. Now let's talk about capacitors. These symbols here of two opposing plates, those are called capacitors, C1 and C2. It's very similar to a battery in that, except that the battery will have a larger one and a smaller one across it. So this is a battery here, and this is a capacitor. The voltage across the battery and the voltage across the capacitor are the same. Because these capacitances are in parallel, the voltages are the same. V over V sub 1 is here. The voltage drop across this capacitor, and V2 is the voltage drop across this capacitor, and they're the same. V1 is equal to V2, and it's equal to V, which is the battery voltage. So the charge Q is equal to capacitance times the voltage. That's something you have to remember. Charge is equal to capacitance times the voltage. So capacitances in parallel are like resistances in series. They simply add like C1 plus C2. So whenever you see capacitances in parallel, you have to get the equivalent capacitance, you have to add them. Now contrast that with this one, which are capacitances in series. Capacitances in series, the voltages add to the total voltage, as you see here, and when they're in series like this, they add like resistances in parallel. And so it's just like resistances in parallel. And this is the potential energy from this circuit, and it's equal to the capacitance times the voltage squared. So let's look at a sample problem. This sample problem reads, a closed iron operates from a voltage of 120 volts and consumes 1,800 watts of electricity. How much current is consumed? This part A. What is the resistance of the heating elements in the iron? That's part B. What rating should the circuit breaker have in order to protect the conductors against overcurrent? So let's take it one at a time. The power is equal to the voltage times the current. So we know the voltage is 120 volts. We know the power is 1800. We know that power is equal to voltage times current. And so the unknown is the current. And we have one equation and one unknown. Then the current is simply 1800 divided by 120, which is 15 amps. And what is the resistance of the heating elements? We know that the power is equal to the current squared times the resistance. Since we now know the current, the resistance is simply 1800 divided by 15 squared, which is 8 ohms. So that's the resistance of the heating elements. The circuit breaker should be rated for 20 amps because your steady state current is 15 amps. You'll be running 15 amps all the time. If you have a 15 amp breaker, it'll trip. So you are protecting the circuit, but you're not able to do any work because it keeps tripping. So the circuit breaker should be rated for 20 amps. It'll only trip when there's overcurrent of close to 20 amps. So when you're just normally using your clothes iron, it will not trip the breaker. And the wiring should be sufficient to have that kind of current going through it. So if it's a 20 amp circuit, it should have 12 gauge wire going through it. So if you're ever doing electrical work in your house and it's a 20 amp circuit in your breaker, then you know you have to buy 12 gauge wire. Don't buy 14 gauge wire or 16 gauge wire. You have to buy the thick wire, which is 12 gauge. Now let's look at another sample problem. A certain motor operates from a voltage of 240 volts AC and uses 20 amps of current. The useful work that the motor provides is 4,000 watts. What is the efficiency of this motor? How much power is lost to heat, or which is non-useful energy? So the solution to this one, the input power is voltage times the current, which is 240 volts times 20 amps is 4,800 watts. So that's the input power. The output power is 4,000 watts because that's stated that the motor provides 4,000 watts of useful work. So if the output divided by the input is the efficiency is 4,000 divided by 4,800, which is 0.833 or 83.3% efficient. So that means that if you have a difference between the input power and the output power, that means 800 watts. That difference is power lost to heat. Okay, let's consider this another sample problem. A Honda 2200i inverter generator has a rated output of 1800 watts at full load. That's the continuous load rating is 1800 watts. It can do 2200 watts in surge. It can surge up to 2200 watts, but its sustained full power is 1800. And it can run this power for about 3.5 hours using its less than a gallon of fuel tank, 0.95 gallon fuel tank according to the manufacturer. If a gallon of gasoline has an energy equivalence of 31,536 kilojoules, how efficient is this generator in converting chemical energy into electrical energy? Is it more efficient, running at quarter load, 450 watts, which the manufacturer claims is capable of 8.1 hours running time. So let's take it a piece at a time. There are two kinds of generators out there in the commercial market. There's what's called an inverter generator, and there's another one called a synchronous AC generator, which are your old-fashioned generators from many years ago. Before these inverter generators became popular, all the generators were synchronous single-speed generators, and they only run at one speed, 3,600 RPM in the US, because it has to be a multiple of the 60 hertz grid that we are operating in. So in the United States, we are using 60 hertz AC current. It switches back and it turns on and off 60 times per second. So 60 cycles, it's turning on and off. It's going backwards and forward 60 times. But these inverter generators are different because they are inverters. They generate DC current, not AC current, and then they invert the DC into AC, and changes the DC into AC, and that's how you get AC output out of this inverter generator, because it's using an inverter instead of an AC generator. So the difference is these inverter generators are DC generators that converts to AC using an inverter, and the old-fashioned generators are AC generators, which are direct to AC from the motor, turning the generator. So let's take it one piece at a time. The solution is energy output is power times time, 1,800 watts, 3.5 hours. There are 3,600 seconds per hour. So this is energy is power times time, because joules per second is watts. So if you multiply it by seconds, you get joules. So this is 22.68 million joules. So 22.68 megajoules. The energy content of a gallon of gasoline is 31.536 megajoules per gallon. And you multiply it by the number of gallons, which is what's in the tank, and you get 29.95 megajoules of energy. So the efficiency is the energy output running at 1,800 watts for 3.5 hours. So that's this number divided by this number. And so the efficiency is 0.757 or 75.7%. Now, the manufacturer says at part load it can run for 8.1 hours at 450 watts, and you so multiply it out, 450 times 8.1 times 3,600 seconds per hour, and you get 13.122 megajoules of energy. So it is less efficient, even though it can run longer. It is less efficient at part load than it is at full load. It's only running at 43.8 efficiency. So let's look at another sample problem here. It's another generator problem, and this one is a conventional generator. So it's a conventional 7,500 watt generator made by Generac. Generac is a very common name for, it's a trademark for, it's the company that makes the generator. So the company claims a 13-hour runtime, and it has an 8-gallon fuel tank, and at 25% load, they say that it can run for 13 hours and consume all 8 gallons of fuel at 25% load. This is not that important, although I state it here. It's just something from the brochure from this generator. How efficient is it if a gallon of gas contains 31,536 kilojoules of energy? Why is it less efficient than an inverter generator? So let's go look through the solution. The energy is equal to power times time. So we have this is 25% load, so we multiply 25% times 7,500, and that's how we get 1875. And then we multiply it by 13 hours, and then we multiply it by 3,600 seconds per hour. We have to convert everything to seconds and joules and seconds. So we have 87.75 megajoules of energy output. The energy content in the gasoline is 31,536,000 kilojoules per gallon, and we have 8 gallons, so we have 252.29 megajoules. So the efficiency is 87.75 divided by 252.29, or 34% efficient. Well, generally, these generators, the conventional generators, are not as efficient as inverter generators, because the inverter generators don't have to run at the same speed because it's generating DC. It can run at the most optimum speed for the load. And since these are conventional generators and they only run at one speed, it's most efficient at that one speed and at that one load. And it was probably designed to run at full load. And so it'll be most efficient at that full load rating. At part load, it'll be less efficient, just like the previous example. At part load, it was less efficient. It was only 43% efficient. That's this problem here. At this part load, 450 watts, it runs for 8 hours, but it is less efficient, 43.8 versus 75.7. And this is 34%. If it was running at full load, it'll run for less time, but it'll most likely be more efficient at that full load. So it just depends on how we match the load to the speed. Now let's look at resistances, how we add them. And this is just a simple problem of finding the equivalent resistance of 3 resistors in series. R1 is equal to 35 ohms, R2 is 47 ohms, and R3 is 12 ohms. If the battery voltage is 12 volts, what is the voltage drop across each resistor? So the equivalent resistance is simply the sum of all these, 35 plus 47 plus 12. That's 94 ohms. The circuit current is the voltage times divided by the resistance. So it's 12 divided by 94. So it's 0.128 amps. And the voltage drops are V1 is equal to I1, which is equal to I2, which is equal to I3 times R1. So you multiply R1 by I1, and you multiply R2 by I2, which is the same as I1, and you multiply R3 by I3, which is also the same as I1 and I2. And that's 1.53 volts is the last voltage. So these are the voltage drops for each one. So that's just a sample of how to add resistances in series. Let's go to parallel resistances. What is the equivalent resistance of 3 resistors in parallel? It's the same numbers as before, except now they're in parallel. If the battery voltage is 12 volts, what is the current across each resistor? So the equivalent resistance, if you look at this bottom part, is 1 divided by 35, 1 divided by 47, 1 divided by 12. So it's the addition of the reciprocals in the denominator, because it's a 1 over the equivalent resistance. So it's 7.51 ohms. And the currents are V1 times R1 and I2 and I3. All these currents will add up to the circuit current. So when you look at combined series and parallel resistances, the key thing to remember is to convert each parallel branch into an equivalent resistance. And when you have an equivalent resistance, you can follow the logic on page 452 of your textbook, and you can solve very complicated circuits just using this rule, converting each parallel leg into an equivalent series resistance. And we'll go through an example of that in class.